Welcome to this lesson on Newton's second law, one of the most fundamental principles in all of physics. This law forms the foundation of dynamics, which is the study of motion and the forces that cause it. Newton's second law connects three crucial concepts: force, mass, and acceleration, showing us exactly how objects move when forces act upon them. Newton's second law is expressed by the simple yet powerful equation F equals ma, which reads as force equals mass times acceleration. This equation tells us that the net force acting on an object is equal to the product of its mass and its acceleration. Despite its simplicity, this equation is the key to understanding everything from how cars brake to how rockets launch into space. Let's break down each variable in this equation. F represents force, which is any push or pull acting on an object. The letter m stands for mass, which is the amount of matter contained in an object. Finally, A represents acceleration, which is the rate at which an object's velocity changes over time. Understanding each of these components is essential to applying Newton's second law effectively. When working with Newton's second law, it's crucial to use the correct units. Force is measured in newtons, abbreviated as N. Mass is measured in kilograms, abbreviated as kg. Acceleration is measured in meters per second squared, written as m per s squared. Using consistent units ensures accurate calculations and helps avoid common errors in problem solving. The equation F equals ma reveals several important relationships. First, force is proportional to mass, meaning a greater mass requires a greater force to achieve the same acceleration. Second, force is also proportional to acceleration, so applying a greater force produces greater acceleration for the same mass. Additionally, force and acceleration always point in the same direction. Finally, there's an inverse relationship between mass and acceleration. Heavier objects accelerate less when the same force is applied. An important aspect of Newton's second law is that both force and acceleration are vector quantities. This means they have both magnitude and direction. The equation can be written with vector notation. Showing arrows above F and A, the force vector determines the direction of the acceleration vector. However, mass is a scalar quantity, meaning it has magnitude only, with no direction associated with it. Let's solve a practical example. If a 10-kilogram object accelerates at 5 meters per second squared, what force is applied? Using our equation F equals ma, we substitute the values. F equals 10 kilograms times 5 meters per second squared. Multiplying these together gives us F equals 50 newtons. This means a force of 50 newtons is required to accelerate this object at the given rate. Now let's solve for acceleration instead. If a 200-newton force acts on a 50-kilogram object, what is its acceleration? We rearrange the equation to A equals F divided by m, substituting our values, gives us A equals 200 newtons divided by 50 kilograms. This calculation yields A equals 4 meters per second squared. The object will accelerate at 4 meters per second squared under this force. Let's review the key takeaways from Newton's second law. The equation F equals ma shows that force is directly proportional to both mass and acceleration. Remember that greater mass requires greater force to achieve the same acceleration. Also, force and acceleration are vector quantities that always point in the same direction. Understanding these principles allows you to analyze and predict the motion of objects in countless real-world situations.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.